Okay, hello everyone. So, uh, these classes this year are going to be complementary to what you saw so far, and basically for the fact that I will focus mainly on numerical methods because lattice QCD as a field, it's a very interdisciplinary, and so it's not just theoretical physics and all it's meant to solve the QCD, but then the way to do it is by using a lot of instruments coming both from applied mathematics and especially high performance computing. So this is these two other pillars here is going to be the focus of my presentation. That was slides, you can find them here at this URL. I give you a second to write it down. It's tiny.cc/ggi-rqcd. You can get these to access the slides and then you can follow up. So, before going into details, let me introduce an outlook of the talk. And what I would like to follow is to drive you through the whole pipeline of our calculations. And I will do this in three parts, where the first, an overlap between the first two is going to be done today and between the other two tomorrow. And the pipeline of our simulation is the following here. So as you understood, we need to compute expectation values of observables. These are very challenging to be computed numerically because we have these very highly dimensional integrals, and therefore we have developed techniques to be able to solve these integrals more efficiently. This is the importance sampling, which is the first topic. This part is what we usually refer to as the real simulation. It's the production of an ensemble. These ensembles represent really only the QCD vacuum. So what we put in these ensembles is only the action and nothing else. This is just really the QCD vacuum and are all the interaction between gluon and quarks, etc. After we've been able to produce the QCD vacuum, the next step in these calculations is then the calculation of quantities, of observables. And each of one of these calculations is independent, dedicated, it requires dedicated techniques, etc. I will focus as of the topic on nucleon structure, but there is much more to it. And for every calculation, you get these ensembles, you compute quantities on it, observables, and you extract expectation values of what you're interested in doing. So. And both these steps are extremely computationally demanding, and they are all carried out on large supercomputers by using high-performance computing. After these two steps are completed, then something less numerically demanding, but more demanding from human time, are all the steps dedicated to data analysis, because we want to account for all possible systematic effects and give physical results that are meaningful and with proper error, and this is another part where a lot of our effort goes to. So here usually we let machine work, you need to prepare the code, then run it, and here you spend really a lot of time looking at these numbers and try to get out features from them. So let's start from the first part, simulations. Let me give you a first outlook of it. So what the topic we are going to focus on is what we refer to as Markov chain Monte Carlo methods. And these Markov chain Monte Carlo methods are used to implement a technique that is known as importance sampling. And our goal is to efficiently compute this integral by producing a set of configuration, UI, that are distributed with a probability provided by the action. So we take this part of the integral, the exponential of the action and the partition function, we name it a probability. This is something that if you integrate it over all u, it's 1, indeed. And this is our probability. We construct configurations distributed with this probability, and then we just need to compute observables on them. So all the difficult part of the integral is done here, and then this is just an average, okay? And this technique is known as importance sampling, is the focus of the first part. There are various challenges I'm going to mention. I will not go as deep as the state-of-the-art algorithms like hybrid Monte Carlo, I will stop earlier, but the first part is to give you an idea of this, okay? If there are any questions, please stop me at any time. So, I think this may be something you're all familiar with. When we want to compute an integral, right, what you may learn in the first years of of your degrees is to compute integrals by simply dividing the integral in equal intervals, computed with various methods, either in quadrature or with boxes, the integral, and you just do what is basically uniformly sampling. So you take the integral interval and you measure the function at every at different points. This is effective, but only with functions that fluctuates not much. If you have an exponential function or something, some weird distribution, etc., that are defined on a big range, like our fields, which are many, here we have billions of degrees of freedom, and they can get any value. If you have these kind of integrals, this is not effective at all because you spend most of your time sampling areas that are not relevant, and all the areas that are relevant are maybe you see them once if you're lucky, or you don't see them at all. So what we want to do is importance sampling. We want to provide we want to sample with a higher frequency the areas that are relevant to our integration, okay? And this is a very, of course, a smart idea, but the critical part of this is to produce a probability distribution of your samples that are as close as possible to your target probability distribution. Otherwise, if you know it's a Gaussian, but maybe it's something very tight, an exponential, etc., and you are just a bit far away, you see immediately the issue. You're sampling a lot an area that then is not relevant at all to your integral, and you're actually making things much worse than uniform distribution, because now you focus on tails of your function, etc., and very easy you can introduce bias, have systematic effects, etc. So the whole part of the first session is how to produce samples that are distributed with a proper probability distribution, right? So we want to be able to produce samples distributed like this. Yes? It's in the space. So importance sampling by meaning means you're sampling with a different probability, okay, not with a uniform probability. You sample with a different probability your integral, okay? So you generate samples in a different area, more concentrated in various areas. But the key point of this to be successful is your probability to match the target probability. So there are situations where maybe you are slightly away from this, but it's still fine. You can reweight. You find ways to solve that. But if you're completely far off, it's useless, right? Okay. So this is there are many techniques that have been developed around this. Okay. But here we are going to see how this can be done exactly. Okay, and the way to do it exactly is via these Markov-Chain-Monte Carlo methods. Okay, so the idea behind Markov-Chain-Monte Carlo methods is to produce a sequence of samples of an integral that are like a chain. So one sample depends on the previous. Okay, and by creating this sequence of samples, we are able to distribute them with a probability that is going to be our target. Let's see how this works. So let's start defining some, having some definitions. So the idea is to have different samples, and the only quantity we are interested in is what is referred to as transition probability. So this is the probability of going from a sample to another, okay? So this is only connecting a sample to the next one. And what we want as a good properties of this transition probability are the following. First of all, this to be Markovian. So depending only on the current and the future, does not depend on your whole history, okay? To be time homogeneous, so to not change as you evolve, to be always constant. To be a probability density, of course, otherwise it's not a probability. So you have an integral over all the possible target, it's 1. Okay, and it's positive. And this is very, very important to be ergodic. So ergodicity means that from one sample, there is a non-zero probability to go to any other possible sample in the state space. So it means that this transition probability doesn't have to be uniform, doesn't mean that from one sample you can go anywhere in X. But if you're somewhere in space, there must be a non-zero probability to be able to go everywhere. Otherwise, if you are not ergodic means you do not have a chance to explore certain region of your space, and then you are, of course, you are doing a mistake in your integral. So ergodicity is very important. If our transition probability satisfies all these properties, then we have a very important theorem that tells us that a Markov chain that is ergodic in the limit of an infinite amount of steps, the probability of this distribution, so after many steps, the probability of how these phi are distributed, it's going to be constant, pi, and does not depend on the starting point. So we have, in few words, a fixed point that is unique for the chain, and this is where always our chain will go to. So after a very large number of steps, we have a unique fixed point and a target probability. Okay, so this is very good because it assures us that we can evolve and arrive to a probability that it's unique. Okay, this is an important theorem, and then from this we can find a very easy way to be able to compute our integrals, and this by adding another property that is not necessary but is sufficient to be able to compute integrals, which is the tail balance. The tail balance is saying basically that we have equal probability of going from phi prime to phi and from phi to phi prime. In few words, that this chain is reversible. So basically you see that these two combination probabilities are equal. So the probability of having phi prime times the probability of going to phi, it's equal to the opposite. And we can see that this is a very easy condition on tau to be able to satisfy our target, because if we simply integrate on both sides over phi, we add here this property that the integral over tau of phi prime is equal 1. Basically, this guy here, if we integrate over phi, it's going to be 1. And so you see immediately that the probability of phi, okay, of phi prime is equal to t times p. And this is basically our fixed point, okay? So by having ergodicity, you can easily prove that a procedure to define the transition probability that satisfies the tail balance and is going to our target, it's the situation where we define the transition probability in the following way. We have two combination probability, the probability of C, that is the probability of getting phi prime from phi. And PA, instead, is very, very important, is where we put our physical information, is defined as the ratio of these probabilities. The algorithm we are going to follow is the following. From a phi, we propose a new candidate, phi prime, and we accept phi prime only if we accept phi prime with this probability. Otherwise, we reject it and keep using phi in our chain, and then we iterate. So this is our transition probability. You can easily see that this transition probability is going to thermalize to our target distribution, that is pi. And what is our target distribution? Our target distribution is going to be the exponential of the action, of minus the action. Okay, so basically this is what we are going to do. We are going to say that this is also very important. You can see here we only need the ratio of probabilities. So in the definition of tau, we only need the ratio of the probabilities. So we don't need to compute our partition function. This guy, okay, this is a bit, maybe I should have used the same notation, but you see, you can connect this formula here to what I had before. Yeah. So in this formula here, the expectation value observable is 1 over z, the partition function, which is the integral only over the exponential of the action, times the integral over the exponential of the action and the observable. So this, it's the same wave here. This is our partition function. Pi is the exponential to the minus SU. right? And by using this transition probability, we are going, the Markov chain is going to allow us to compute expectation values of observables of this kind. Okay? And so this is very important. This is exactly how we do simulation. This is known as Markov chain Monte Carlo with the Metropolis hashing algorithm. Okay? And this is what we are going to implement now. We want to try to implement this. Okay? Any question? Okay. A good question is, how are we sure that this now is going to give us an unbiased result, a correct and unbiased result? The only way to be sure, so there is a theorem, so this should be mathematically correct, but as far as all conditions are satisfied, most of the conditions are easy to satisfy in the way we define it. The hardest one to condition to satisfy is the ergodicity. So to ensure that our, in a finite amount of steps, our integration, our Markov chain, has the chance to visit the whole state space. If this is not satisfied, and this is a bit the challenging part of our calculations, then we may get stuck in some area of this integration and then don't go out and again introduce a bias and the wrong result. So, I mean, in the way in which I use. Sorry? In the way in which I use the dead balance theorem, which is basic standard just quantum mechanics. You need this phase space factor. Yeah. Here you assume that you have the whole phase space. Yes, well, it's already, the phi is already, it's limited to your space, right? So you have... no, but you have, yes, exactly. So in this equivalence here that you have, which is the phase space of the two terms? Is there a... No, there is no, because you have, well, it's the probability of phi, so it's... no, it's actually the probability of phi. So the probability of phi to exist is non-zero in the phase space, right? So the fact you have this probability of phi, if you are outside. Yeah. When you use the detailed balance for reaction, for example, you have a cross section, and you say that if it's in the initial state or in the final state, provided you put the correct phase space, you have this equivalence. You can look from the initial to the final, but if you took the final as the initial, you would get the other one. Yeah. Is this the same? It's the same, yes, it's the same. And I think it's within this probability here, the probability of phi to exist. Right? Because, okay, so what I was saying, yes, what the very important thing is to be ergodic and to go around. And this is critical, and the critical point is autocorrelation, because in this Markov chain Monte Carlo, as you may understand, one sample is correlated to the next because you are a chain. So you don't have independent sampling. But your final goal is to generate independent sampling. And this is critical because if you want to go to compute the variance of an observable, by the way, by square here I mean an observable, right? So if you want to compute the variance of an observable, in a standard variance formula, you have the expectation value of the observable square minus the expectation value squared, okay? Because very often you can ignore cross-correlation terms between various samples by saying they're independent. This is zero. By saying that the sample done at different time is independent, and therefore any cross-correlation term is zero. In our case, this is not true because a new sample is dependent on the previous. This is what we refer to as autocorrelation. And so if this autocorrelation is very large, it takes a lot of time to decorrelate, is going to affect our error. And therefore, the correct formula for the variance is the ability, is the standard variance times the autocorrelation, the integrated autocorrelation time, tau int, that we have here, which is defined as the this autocorrelation in time between observable, which is an integral over the normalized autocorrelation in time between observables. And we can see how this looks like in our simulation. So for center observable that we are computing, like take a plaquette, these decorrelate quite fast. So you can see that after 20 or 30 steps, it's almost decorrelated. A plaquette doesn't look similar to the other. But there are very specific quantities, like the topological charge, that takes a huge amount of steps to decorrelate. And this amount of steps in our simulations becomes worse and worse as we go towards the continuum limit. So as we go towards the continuum limit, we risk more and more to get stuck in some part of the state space, and thus to not be able to sample the quantity properly, and have either a large systematic error or a bias. Okay. And you can see, for instance, here how going towards a equals 0, so our continuous limit, this grows exponentially for instance, for a topological charge. It grows exponentially for all of them, but for certain is much better than for others. Okay. And so this then, having a very large autocorrelation times, means a very large error, meaning that you need to do a really lot of steps to be able to sample a quantity properly, etc., etc. Okay. So in all the observables, in all our results, we make sure that our configurations are independent, etc., and this is accounted for. But there are certain specific quantities, like topological charge, that are extremely difficult to sample. Okay, so this was an introduction to all the theory we need to be able now to perform simulations. And what we are going to analyze is something extremely simple, that is a one-dimensional harmonic oscillator. So this is something you're all familiar with. It's one dimension. We are going to have a string. This string can get at every time step a different value. And we are going to, we want to solve this, this action, okay? This system. We want to study this system. So this is our continuous action. We have a velocity, a kinetic term, and we have a potential term. And once we discretize it, it's straightforward to understand it. If we discretize it, we have basically the derivative is the difference between two nearing points divided by dt square. This dt square, this is not squared here because one of them simplifies the t of the integral, right? So it's only divided by dt. And our potential term is just x squared at a given position. This is our discretized action. And our goal is to compute an expectation value of observable, like for instance, expectation value of correlator, which is the correlation in time between x measured at 0 and at a different time. Okay, so we want to measure this correlation, which we know already that this is the result from the continuum limit, which is an exponential decay in time with the frequency, etc. Okay, so this is what we want to do as a first exercise. For this, we are going to use Google Collaboratory. We are going to have a Jupyter notebook here, and please open your laptop and open the notebook. Okay, so you can copy and paste this URL. When you're all ready, I start. Okay. Okay, you all open the notebook, any issue with that? Okay, fine. So, I think you used Colab again in these classes, but okay, you have only view only on this notebook, so the best is that you create a copy of it. You can easily do it by clicking here, File, save a copy in Drive, and then you edit it, right? But if you don't have a Google account or Google Drive, you can open it in playground mode. My suggestion is to create a copy, so what you do, you don't lose it, and we go on. Okay? So, I will start introducing a bit what I wrote for you here, okay? And the implementation of it. And then there are a series of tasks, exercises here that I would like you to implement. And then later we discuss the solution to it, and I will be here around for any question you have. Okay? So, well, the theory, we understood it. We have this is the action, the potential again. This is just for you, for your reference. The discretized action, how it looks like. The definition of the correlation function, and the target result. I think here, there are any questions on the system we're going to study? No? Okay, let's look a bit at the implementation of it. Okay? So, let's start from here. Do you see well, or shall I zoom in more? It's okay, I think. So, the action. In the action, we need the following parameters. We need the mass, the frequency, and the t, the step. Mass and frequency are okay, are parameters that you do not have any physical meaning here. You cannot connect them to, there are no physical units, right? You need, it's a ratio of them, right? In the same way as the time does not have any physical units, but you can measure anything in terms of ratios, okay? And these, our continuum limit is then defined by this time that becomes smaller and smaller, right? So this is where our lattice is going to get finer and finer. Here you see an implementation of the action. How many of you are you all familiar with Python? Yes, who is not? Oh, okay. But you use Python a bit in the previous days, right? Yeah. Use it. Okay. So, okay, sorry about that. Let's dive a bit in. So, I will be more pedantic in the explanation. So, okay, you know, NumPy is the package we use. It implements all the various numerical tools. And okay, this is, I think it's quite readable, but of course, if you're not familiar, it's easy to do mistakes. Regardless, what we are doing here, it's these are the terms of the action implemented directly. We want to sum, there is a sum here over all possible positions. And x, okay, x, it's our array, so you need to think this as a sequence of values. This NP sum is going to sum over all values. And for instance, the way I'm using here to implement the final difference, okay, here, is by rolling our array x of 1 and subtracting x itself again. So basically, to give an example here, if I if I have if I import NumPy, I can say np.arrange 10. This is going to generate 10 arrange of values 10. Just a second to connect. This is going to take a bit of time to connect the first time because you need to get a node. Okay, it's taking a long time now. Okay, it connected. So now only the first time, then everything is fast. So and p-arrange 10 is going to generate, for instance, 10 numbers, and if I want to roll it, when I do roll it, this is assuming periodic boundary condition, that is what we have in our case. We consider periodic boundary condition, and so you see that everything is shifted of 1. And so when I do this minus itself, x minus itself rolled, I'm doing the finite difference at every point, because I do it to array, I'm doing finite difference, right? So this is how I'm implementing the finite difference efficiently. You need to be aware that Python is a very slow programming language. Is interpreted. So you will want to avoid as much as possible to do any for loop on data. If you want to, you can write it as for I in x and do the finite difference as written here, but this is much more efficient because I'm telling you also a bit about high performance computing, that is what we care about. When you have a big number of data, okay, a large number of data, what NumPy does, it's going to deploy all the calculation to compile code and performs them at machine precision, like a C code normally, okay? So the MP sum, it's not a Python code that is going to do the sum element by element, so for loop and a special for loop, but it's just a compiled C function that is going to sum overall values. And the same, the roll, etc. So all operations done via NumPy array are done very efficiently. So this is, for instance, the finite difference. Then here we are computing a square. We sum it again over all possible x and multiply by the coefficients. Okay. And our action is kinetic plus potential. This is the action for a given x. And here I'm giving the parameters. Okay. The next part, the next task we need to do in our simulation is to do a Monte Carlo step. Let's go a second back to our slides. What we want to do in this Monte Carlo step, this is in practice, we have a current candidate, a current value of x. We want to propose a new one, and then accept it with this probability. So let's see a second what is this. The proposal of a new value, okay, we are doing it, for instance, like this. We have on the coordinate I, we update the current value that we have. So this is a string that can have any value in x. Okay, we are going to update the current value of the string, the current position in time, by adding a random deviation. This again, we need to propose and change with a certain probability. So we take a uniform distribution. Okay, right? It's a uniform distribution between minus epsilon and plus epsilon, and we get a value somewhere here. This is 0. We get a value somewhere here, and we update the value. So the value goes from x to x plus minus epsilon something, uniform probability. And this is going to be a random value. So this is going to be a random update. This is, in the Monte Carlo procedure, everything is random. Okay, so this is a random update. And this is the first ingredient, where this is the uniform probability between epsilon and minus epsilon is, in practice, the PC. So this is with our probability to go from a point to another. Okay. The other probability we need to implement is PA, that is probability of accepting this change. The probability PA, right, before I could have used the blackboard, I will do it now. The probability PA, sorry, yeah, we define it as the probability is defined as the minimum between 1 and the ratio of our probability done on phi prime divided by the probability of phi. So this is a step you can easily do. Maybe it's good to have a clean board. Okay, so this ratio, our probability pi of phi, it's what we defined as the partition function times the exponential of minus the action measured of phi. This is our target probability, right? The ratio between two probabilities is something very nice, because if I do the probability of phi prime divided by the probability of phi, you can easily see that the partition function cancel. You have the exponential of minus s of phi prime, okay? The other exponential is the denominator, so you bring a numerator, it's a product, you sum it, it's plus s of phi, right? It's a ratio of exponential, you bring it up, and it's okay. Let's collect the minus in front just like this. And what is this? This is the difference of the action between phi prime and phi, okay? So our acceptance rate is given by the ratio probability, which is equal to this, okay? So what we need to compute for computing this probability PA is the exponential of the different induction. So we want to compute the different induction. How do we compute the different induction? Before updating xi, we compute the old action, right? This star param, it's something that Python allows me. So this is to do, it's an expansion of parameters. And basically, you need to think this param as a dictionary that has these values in here. And I'm passing them through. So I don't want to explicitly write all the parameters here, but I just collect them in params and pass them through. I will show you in a second how this works. Regardless, these are going to be these parameters, okay? And this is the old action. I update the field. I'm storing here the old value because I need it for after, but I update the field. I compute the new action, and the x, delta x, is of course the difference between the new action and the old action. Now, I need to accept the move, okay? Let's go back a second. I accept the move with a probability that is the minimum between 1 and this exponential. Why there is a minimum function there? Yes? It's going to be greater than 1. And a probability function is needs to be always maximum 1, right? So this exponential of minus delta s is something that, of course, like he said, delta x is here. It's something that does like this. Yeah, it's 1. A negative delta s, which is something we want, it's good. It's good that they actually decreases because this is quantum mechanics. Sorry, it's, yeah, it's, anyway, Hamilton mechanics. This is our action, and basically what we are saying is that if the difference induction is negative, we always accept. So this is going to be our probability A, right? Yes. Sorry? I didn't understand what method. Yeah, so exactly. Exactly, that's the point. So what we are doing is that we have this distribution, okay? So if it's negative, we always accept it. If it's positive, we need to accept it with a probability, okay, that needs to take into account delta S. So the way to accept it, so basically the probability is accepted if NP random rand is going to create a random sample between 0 and 1. So it's any value that is between here. So if this random number is smaller than this probability distribution, okay, here I'm not considering 1 because it's always going to be smaller than that in that case, I accept it. If it's larger, like here, I reject it, okay? If I reject it, what I need to do? I need to use the old phi. And so I'm going to replace xi with the old xi. That's why I stored it, because I don't want to lose it, because if we reject the move, we stay there. Okay, so if we go somewhere, your intuition is that if we go somewhere where the action increases too much, okay, we reject it. But this is not classical mechanics. We don't want just to find the minimum of the action. This is a statistical mechanics process, okay? So, like with a Boltzmann distribution, we want to accept the action that is larger just when, with a probability that it is e to the minus delta s. So we allow the action to grow. We don't want just to minimize it, but we allow it to grow just with this probability. Okay, perfect. This is the Monte Carlo step. This is what we do. And basically, the best way to do it, just to increase the acceptance rate, this is all to do to be able to increase the acceptance rate, is to have a limited epsilon, so you don't want to allow it to move too much, because if you just update x randomly, then you may have a huge difference in the action and go completely somewhere else. Okay, so this we have a limited epsilon. And we do it for one, you need to think about this thing. We take a point per time and try to change it a bit. So we take a point per time, try to change it a bit, and then keep going, and this will let it evolve. Okay? You can do some animation of this, how this is evolving if you want. Okay, and this is going to allow this to change value. All clear so far? So if you have then any question specific about the code, you can ask me later. So this is one step. One step is after we updated all the indices, okay? The indices, I'm taking them randomly. I shuffle the position just to don't change the string always in the same order, but in a random order. Okay, this is one step. The Monte Carlo simulation then is going to be given by something that starts from an initial path. This is our initial distribution. We said by the theorem we didn't demonstrate, but we mentioned before, our final distribution it's not affected by the starting point. So we can start from anywhere. You can try to change it. You can start from random numbers or from 0. You can start from a distribution, and then this is something that has 0 value everywhere, and then we try to update it. Okay? So we do a Monte Carlo step, and we do it as many times as we want up to complete the integral. Of course, we cannot keep going forever, otherwise we will never have a result. But you define a number of steps large enough, 5,000, and we keep going. If you see here, I'm distinguishing between two parts in this integration, something that is the number of steps, how many we want to integrate, and then a thermalization. In our simulation, we are always we may be affected by this thermalization effect, because like we discussed here, we start from somewhere, but this somewhere can be anywhere in the position space. We don't want to be affected by it. It requires a certain number of steps to be able to thermalize and arrive to this condition, where to arrive to the fixed point where we have the target probability. So the thermalization is to account for this. You're starting from anywhere you like, is your initial solution. And then you do some steps until you arrive to the target, to the fixed point, and then from there you integrate. You do not want your result to be affected by the starting point. Okay, this is why we refer to this as thermalization. You need to thermalize the system. Any question up to here? So this guy here now, this function Monte Carlo simulation, is going to return us samples of our final result. What we are left to do, so this is going to provide us the configuration that is distributed according to this probability. Our final goal is to compute correlation function. So how do we compute the correlation function? We take now, this is really the last function I have here. A correlation function is now the correlation between the value of x measured at a certain point 0, or let's say at a certain point t prime, up to x of t prime plus t. okay? For any t prime. So we are interested about the distance. We are interested about the distance delta t. So we want to go to a certain distance delta t and measure how the correlation changes with a certain distance. So 2 points, you can understand that 2 points in the harmonic oscillator are correlated. So the value of this is correlated by the value of the other point because this is, they are connected. Our action is not fully local, but depends one on the previous, right? So you have a finite difference. Okay, so this is our correlation. This is a function that computes a correlation. You can understand it's again like before. I compute the correlation between 2 points separated in time by rolling it. So I do x, I do a copy of x rolled by t. I multiply them, and this gives me the correlation. And I mean it because I do the average over all possible t prime. So this is the distance. This is going to be the distance. And this mean is that's the average between all possible separation of the certain delta t, right? Because anywhere you are, it's independent. This is a translational invariant system with periodic boundary condition. And so independently on where you measure it, the results should not change because your action is translational invariant. You can see it above, okay? So this is why I can average, because this is a symmetry of our action, of our system. Any question? So these are the functions. If you have a specific question, we do it. Okay, what we are left to do is to run a simulation. So we define our parameters. N is going to be the number of time sliced. This is going to be the distance. This is going to be the mass, the omega. These are a bit redundant parameter because you can see if you can redefine everything and group. You can, for instance, define m divided by delta t and then m times omega. You just need 2. You don't need 3. They are connected to each other. So you can find combination. Basically, they're redundant, but regardless, you can we define all 3. Epsilon is how much we move in this random walk. These are the number of steps of the Monte Carlo. These are the thermalization steps. Okay. You can take the code, run it. So you define these functions. You run it. And what I'm going to do here, I'm going to take, you see, this is a set of parameters. I pass them like this with the expansion of these values. Okay, star params. I pass them to a simulation. The simulation is going to run. You see now it's going to take a long time, okay, to produce all these samples. And then I'm going to get the correlators. Okay? Once I have the correlators, yeah, it takes a long time, but you will see that after you do the exercise, this is going to be much faster. Okay? This is why we have the exercises. Yeah. Once we have this, we are going to plot it. Okay, we didn't run yet, but anyway, I go directly to the plot. We are going to plot the correlator, and we can plot this correlation function in time. I'm going to show here our result, the expected result at the continuum, and how this matches. Okay, okay, it has run. You see, it took 58 seconds, almost 1 minute. And we can plot this correlation function and obtain this result. Is this, maybe now let's put it in a log scale. Okay, it seems to decay exponentially, but it's doing some weird stuff. This is the average correlation function. There are no error bars. I'm simply averaging over all measured correlators in this integration time. So I'm just really doing the integral. I'm just really doing an expectation value without worrying right now about the error on it. So here, here we discussed the error, but now I just measured the expectation value, the mean. I average over all of them, and I get this result. Let's plot it in a log scale to see how it decays exponentially. And we see something like this, something that at the beginning resembles our continuum result. Then it does weird stuff here, and then goes up again. Okay. Is this what you expected. Of course, it's very far from our final continuum result. So, what are can someone explain what we are seeing? For instance, why is going up again and doesn't decay exponentially? Anybody guessing? An intuition of why it goes up? Because of the periodicity, very well. Well, as I said before, this our action that we did now, it's a periodic lattice. So our lattice starts from here, moves around, and then this, it's exactly the same image. So if you move the time here, it's actually a bit misleading because the time is not just growing. We start from here t0 and we go up to 10, let's say. Okay, we have 100 point a step of 0.1. We go from here 0 up to 10, but actually when you're starting from here at 0 and you move forward, the final of the lattice, you do not see it, it's not at distance 10 actually, but because of periodicity at distance -1. So going forward or going backward, you feel it's the same. This is why the function goes up again, because the correlation of this point with this one here, it's not a correlation that has a distance 10, but has a distance 1. Right? We're going back 1. And this is why this the symmetric and this result on the on one half, it's equal to the other half. Okay? Because going forward, going backward is the same. Very well. Why is doing this wiggling then? Then what we would expect is the decay exponentially up to here. Why is doing all this wiggling in the middle? Because our result is not final, it has statistical error. I would like to run the simulation again, but it's going to take another minute. You will have a completely different result if you run it. You will have a result that is very equal at the beginning, but then it does these fluctuations again. Why? Because there are statistical errors that we need to estimate. Okay? And the only way to reduce statistical error is to run the simulation longer. It took 1 minute to run this. You want to run 10 times more statistics, takes 10 minutes. So you don't want to do it right now. You want first to start, before playing with it, with the tasks we have here. Okay, I let you go through them, or you want me to read them?
Sorry, but is there a chance that you running it for as long as you get the exact result?
Well, you get is the correlation function, you will get something that decays exponentially. That you always get it. Now that you get the exact results, this is a continuum limit. So you need to do an analysis where you take the continuum limit of this integral. And this is a very good question. I will discuss it later. But if you want to take a continuum limit of this, you want that final result, it is the correct one when you have infinite volume, so an infinite times extent, as well as a zero lattice spacing. And you understand that going t to 0 and t capital to infinite, it's a very big problem because these are two limits that are require one to increase the number of points and the other to even increase further the number of points. So this is a v-square problem because as you reduce the density, you need more points. But if you want to keep your volume constant or you want to make it large enough, you need to increase even further. So your total number of points is given by t divided by the t. This is the number of points, okay, of your theory. So if you make this smaller, the number of points has if you halve this, the number of points has to double. If you want to double the volume, this has to double too. Okay, so this is another point where so you're going to get something. It's a correlation function. It's a finite t. It's a delta t. Yes, you take the limit that goes to 0, but it's a small delta t. It's not minus. It's a delta t. It's not a. No, I don't mean the differential. I mean something. A delta t can also be 1. It can be big, a delta t. Delta t is always a difference between 2 times. By small d, I mean that it's something finite but small. So when you define delta t, this is just t minus. Yeah, and they're saying the physical volume is bigger. It's
Is there a dependence on the frequency?
like we said, you need to define your scale, right? So basically, we do not have a scale. So in this case, you have two adimensional quantities that are the mass divided by the time and the frequency times the time. So it's you have adimensional quantities, and then you define the scale. It's always proportional to scale. Very good. Okay. So now the time is 27. We did already an hour. Wow, okay. Let's, I want to give you a bit, something like half an hour to do this. Okay. Then we will look at the solutions. Okay. And then we finish. I will go back to the presentation, do a bit more, and then we finish. So I'll read them. If you want to take let's combine this with a break. So if you want to take a break now after, it's up to you. Let's start again at in half an hour, so at 4. Okay? And I will be here. And you ask me questions. Okay?
So you want to start again at 4?
At 4. With the half an hour with the first bit of theory more. I will.
No, half an hour break.
It's not break, it's exercise. No, yeah, you don't, as much as you can. Then I will give you solutions, okay? Yeah, okay? So this is a very, it's highly inefficient because if we compute the action difference by computing the whole action instead of only for the terms that have actually changed, we are doing much more work for nothing. We are computing a lot of zeros, right? So the first task was asking you to write a new function that only computes the difference for the specific height side that has been updated, where we are providing the old xi, the I value, and for this we need to compute the difference. And this, it's easy to do it. Basically, you can see that, like I said, for the potential, it's only the difference between xi new minus xi old. While for the kinetic term, you need to be careful because your old xi appears in few terms, being this the difference between I plus 1 minus xi, this is the derivative squared. The site I appears either here or here, so there are 4 terms, the old and new. And here are these 4 terms. So it's where the old xi appear on the left or appears on the right, and this is the xi, right? So this is all you need for computing the action difference. You don't need to compute the whole action. So if your system is very big, the action difference of updating only a site I is local. It needs only information about the neighboring points. Okay? So this was the first task. And this will make your code already more efficient. Okay. Another step now, it's about doing performance optimization. So in Python, like we said, loops are very inefficient, but there is a very simple way to accelerate your Python code that is doing loop over data, and this goes by just-in-time compiling your code. So there is a package named Numba that provides a decorator and JIT that you can use simply to decorate your function. Okay, like here, this is a Python decorator. And when this function is called, the first time this function is called, just in time means that it's going to be done just in time at the moment you call it. At the moment you call it, this function is going to be compiled. I don't know how many of you are familiar with programming. How many of you are familiar with programming? Do you know what compiling means? Yeah? So you have Python, it's interpreted, you don't need to compile anything, it just runs. A C code, you write the code, then you need to compile it. After you compile it, you produce machine code that is going to run very efficiently. Python misses this step. This decorator here does this step for you. So for instance, this it's going to compile this function, it's going to turn it in a C code, compile it, and make something you can call. Okay? And what makes sense to compile is this Monte Carlo step. For this, we need to compile all the functions calling like action diff, because this Monte Carlo step is done for every individual site. Okay? So we have here a loop over the data. This is a loop as big as your data size. Okay? Subtlety is that we had to remove all the params that I had here before, because although they were very nice, Numba does not support them. So you need the parameters explicit, and this is why the parameters are explicit now. Okay, this was task 2. It just, okay, we had to put this decorator. Then 3, I will not go through, it's a matter of seeing the thermalization effects. This we can, you should try it at home if you didn't. Acceptance rate is another important observable. We want to make sure that our that we are accepting that our integration is proceeding. So if we accept always, either means that we are not moving a lot because epsilon is very small, so that's easy to accept it always, or yes, that's mainly the reason why we accept always. A good acceptance rate is something that is above 50%. So you want half of the time to accept and half of the time reject, somewhere above 50%. You don't want it too high, because too high means you're not moving, or that your action is trivial. If instead it's too low, again, you're not moving, but you don't move because you don't accept. So in one case, you don't move because your epsilon is too small. In the other case, you just stay stuck somewhere. So you don't move. So you want to move around. It's important to measure the acceptance rate. So this Monte Carlo step now, it's returning the average acceptance step over all the updates. Okay? And you measure it by just counting how many times you accept and divide by the number of steps. Okay? So this it's acceptance rate. We need to do it. And you can try to see what is the effect of changing epsilon. So if you make epsilon too small, it's very high. If you make it too large, it's very small, the acceptance rate. Another key feature that we said, something that's very important, it's ergodicity. Although it's not an issue in this simple case, but it might be an issue in other, is the update that I did with a uniform step really ergodic? So the fact I'm updating ergodicity, if you want a reminder, means that you have a non-zero probability of going from phi to any other possible phi prime. Moving of plus minus epsilon is ergodic? Is it ergodic? Sorry? Yeah. Well, it depends how far you go. I mean, after many steps, you can go anywhere. You need to be accepted. But these should be satisfied between every step. So does this satisfy ergodicity? The answer is no, because your x can only go from minus epsilon to plus epsilon. Okay? It's 0 everywhere as the probability, but can go uniformly there. But again, it's effective because if we do not put boundary, we just make a uniform distribution between plus infinity and minus infinity, it's what we just discussed above, we will go nowhere because we never accept, right? We need to be somewhere close to zero. What would be a good way to satisfy ergodicity still without changing too much this effect by still having an epsilon? What is a good way? Perfect. To do use a Gaussian, or to use any distribution that is that has a support everywhere, right? effectively a Gaussian, you have zero probability of going farther than 3 epsilon. You know what is the probability of a Gaussian. You define an epsilon. Epsilon, it's in this case of random n, if I multiply by epsilon, this is going to be the standard deviation. You know that you have infinitesimal probability of going above 3 standard deviation, etc. Right? Already going farther than 3 standard deviation, it's impossible. But it's an effective way for theoretically saying that your integration is ergodic, although in practice it's the same thing. In practice, you have zero probability of going very far. But still, you can say that is greater than zero, the probability, although it's close. But it's greater. It's never zero. Okay, so we changed it to Gaussian. This was ergodicity. Now, these were easy things. A less easy task is to write the function that computes the autocorrelation. I'll give you a solution here. Of course, you need to just take the formula and compute the autocorrelation in time. But an easy task instead was the periodicity. Maybe I should swap them. The last one was optional, but up to here you could have managed. Periodicity, it's good, like we said, to symmetrize it. Now, let's take the new code, compile it, and I want you to appreciate how fast it's going. I will tell you a bit more about this, but let's compile it, and let's run exactly the same simulation we have run before. Are you ready? I run it, and wait a second. It's done. Okay, for a second, it's bad. The first time it took more because it compiled. I ran it again. It's done. 0 seconds. Okay. Why is this fast? Because we compiled it. But it's exactly the same effort. Now we can truly start increasing the number of steps. So we make 10 times the number of steps, and instead of taking 0 seconds, it takes 2 seconds. Okay. You can now if you try to plot the thermalization, you see 1,000 steps are more than enough to thermalize. There is no effect, so you don't need. You need just 100. It's okay. But you can increase the size, of course. Like we said, if you increase the size of a factor of 10, this becomes 10 times lower because we have 10 times more the number of points. Okay. We increase the number of steps, and we see that our final result now, okay, we symmetrize this also, now starts to be nice. If we go longer, you can see that all these fluctuations, they become less and less severe as you go longer. And if you truly compute the error on it by computing the autocorrelation time, now I say a few words about this, but just to show you, the error on the quantity is actually like this. So you see that these fluctuations are just statistical. So this is only the region where your result is precise. And the only way to decrease this error is by doing more and more and more steps. So you let it run for an hour, and then maybe you have something good. Okay, but this number of steps is not enough. Okay, so here you have the whole solution. Let me say a few more things about what you have here. The correlation part, I did some more work. This is extra. You could have accelerated the code by just compiling it with ngit, but actually there is a much, much more efficient way to compute correlation functions. I don't know if you know about it, but this is by doing a fast Fourier transform. So fast Fourier transform had the benefit that your problem, computed correlation functions will scale like n square, so you increase the number of points, and this scales like n square, so the time it takes, because you need the correlation between all possible combinations, which is n square, of course. But a more efficient way to compute the correlation function, it's by using a fast Fourier transform, was numerical effort increases with n log n. This is much faster, more efficient. And you can study a bit the literature. We will not go into details, but basically you can compute this by doing a fast Fourier transform forward. You compute the power spectrum, and then you do an inverse Fourier transform, and this gives you the correlation. This is coming from this theorem. And this is the way I'm computing correlation function here. So I do a fast Fourier transform forward, I compute the square of it, and then I do an inverse Fourier transform, and this is the correlation. I muted myself. Okay. Okay. This is a function that symmetrizes the correlator, and this is a function that, with the same trick of fast Fourier transform, computes the autocorrelation. So the autocorrelation now, it's what we said before. The autocorrelation is the fact of, it's again a correlation, but it's not simply the correlation between x a certain t and x a t plus 1, a t plus delta t. Okay, it's not simple this. The autocorrelation, we care about how the sample we measure on a certain configuration I is correlated with the sample we measure on a configuration J, okay, on a different step. So it's, you see it, if we go back to the slides, this K here is not the time of our lattice, but it's the time on the Markov chain. This is what we refer to autocorrelation. It's still a correlation, but the word auto means that is in time, in the simulation time. Okay, so and basically what you see if you compute the autocorrelation is that okay, we have run a lot now. We run 50,000, but if we run less, we have an integrated autocorrelation time of 618. So basically, it takes 600 steps for our correlator to decorrelate. So actually, all this time we do, we just do small steps in epsilon. So you can find the optimal epsilon to minimize the autocorrelation time. That's your final goal. The final goal is to find the optimal epsilon to minimize the autocorrelation time, because means you're moving the most effectively around to sample. Okay. 618, it's a lot. We do every 600 step, we have actually a different sample. All the rest is correlated. It's always the same because you move less. And this is why we have very large errors. So you can try to change epsilon. Let's try a second. But okay, you can do a bit more practice on this. So if we make our epsilon smaller, what you should see is that if we plot the acceptance rate, etc., should be better. But you saw the result is much worse. And you see that the autocorrelation time now is 4,000. This epsilon is tiny. And you see that this correlation function now it's awful, but it's awful because, again, we are not putting error, and with these 4,000 steps, our errors are actually huge everywhere. They're a bit underestimated here, but they should be huge everywhere. Okay. Instead, if we try to do something different, we try to put an epsilon that is 0.5, that is larger than before. You find that the autocorrelation time, it's much smaller, it's 126, meaning that we sample much more efficiently, and thus our errors are smaller. Okay? You see, we are decaying very well, very similar to the continuum. Okay, this is a nice exponential decay. This is a logarithmic scale, right? But we are a bit far. If we want to improve how far we are, what do we need to do? We need to go towards a continuum, so make our volume bigger, etc., account for our effects. You can practice more and you try to have a final result. Okay? So, let me take advantage of this to say just a few more words on what we do, on the history of what we did, to summarize also the talk, and then we continue tomorrow. So basically, this was a simple example, okay, of what we do. What we do is much more complicated because, first of all, we have gauge degrees of freedom, okay, the gauge field. Gauge field, how many degrees of freedom does have an SU3 configuration? Do you know? So for a single link, how many degrees of freedom do we have? We have this SU3 matrix. The SU3 matrix has 8 degrees of freedom. These 8 degrees of freedom are, let's say, the generators of, you can write this matrix as CA, TA in the algebra, in the Lie algebra. This what we want to change is these coefficients. Okay? So our configurations have 8 degrees of freedom that we're integrating over. Then this link, if you follow what Dina told you, or anyway, you know a bit about lattice, these links are positioned on, sorry, the link. These matrices are positioned on the link, not on the site. our lattice, because these matrices kind of represent, if you want to think a bit about it, I don't know, like general relativity, these matrices represent your matrix, how the matrix is changing from a point to another, and it's the same. This is a rotation. This is a rotation in the color spin-off field. So when you go from a point, your psi fermion goes from a point to another. This is changed by, it's related to the neighboring one in direction mu by u mu. So it's this is the pull backward of how this is on the lattice. And so basically, the fermions that are positioned on a site are changed around by the gluon fields that are connecting different sites. Okay, so the gluon fields are put, the SU3 matrices are put on the links. In 4 dimensions, that is the theory we simulated, which is space and time, the number of links are 4 per point. So every point, for instance, 2 dimension, every point has only 2 links. Although it has 4, the other 2 belong to the neighboring one, so it has 4 links. So 8 times 4 are degrees of freedom per site. Then what do we have? We have the volume. This is the volume, which is again 4-dimensional. You have, usually we represent it as L to the cube times 3, times time. If you put in some numbers, already this number, there 4 to the cube times 8, this is already quite huge. It's already order of thousands. Yes, degrees of freedom. But what we do, so this is why these things are numerically demanding. What we did before was a very simple example. This theory is much more complex and much more numerically demanding. And so you can start simulating these small ensembles quenched, and this is what began in the 80s. This is where the first simulation. For this purpose, you had some first supercomputers created, dedicated computer for it. For instance, it's famous the APE computer that was built here in Italy, in Rome. And this is how the simulation were performed, and then some bigger machines came out, and first results of lattice QCD came on. A very big issue of doing quench simulation, like we discussed today, is that you do not match the expectation of the results measured by experiments, because you don't simulate fermions. Introducing fermions, it's much, much more expensive, it solves this, but you cannot use simple Markov-Chain Monte Carlo like we did now, but we use HMC, that stands for hybrid Monte Carlo or Hamiltonian Monte Carlo, and we use molecular dynamics to be able to move from a configuration to another. But this allows us to simulate fermions, the lattice size grew, and you can show that you fix all the issues you have once you start including fermions, and things work well. And this it's about in the 2000, okay? And then the theory proceeded. You want to simulate more fermions. This is a bit more challenging because the degenerate doublet, it's easier to include. The non-degenerate one, it's harder. If the strange has a different mass than light and down. It requires more algorithms, more stuff, but you can proceed. You can increase the volume of the lattice, etc., etc. And what we do nowadays are very large lattices. This is actually still small. Nowadays we do this kind of lattice size. And if you try to plug in these numbers in this formula, you have really a billion of degrees of freedom, etc., that you need to integrate over. And this is why it's very critical to produce configuration. You produce them once. It's very expensive. But then once you produce them, you can measure stuff. And we create this set of ensembles that then we compute observables. Tomorrow we continue on this. Yeah. And we see a bit how we measure correlation functions, and I give you another exercise like today, okay? We will continue numerical methods. Any question? Okay, if you want to try to review the code, I mean, I think it's a good pedagogical code also from the Python point of view, so if you want to try to look at it, it should be nice. Okay, thank you, see you tomorrow. Okay. Yes, question, sorry.
Would that be possible to change the potential?
Of course, it's extremely...
I mean, I'm sure it's possible, but the question is, would it be too risky for them to try the potential?
That's extremely interesting, yes, because for instance, what we did is the harmonic oscillator, but a system that is very interesting is the anharmonic oscillator. you need very few changes in the code, but basically what you want to do is for an harmonic oscillator, instead of having a potential that is just a parable, you can introduce an x to the 4th term. So you have your potential, it's something, a coefficient alpha square plus beta x to the 4. And if you play the coefficients well enough, you can break the symmetry and have then an American hat. Sorry, Mexican. Anyway, a double wall. And this system is very interesting because what will happen to you if you start doing this simulation is that if you increase the depth of this well enough, and you start getting stuck here, and you will never be able to go there, right? And this, it's a big issue of simulation, and you need to, this is a typical example where when one can study ergodicity, etc. Because if this, you can study the potential, basically if you will see very nice things that if while here you will see that the x in average, the expectation value of x square, it's around the minimum. Here you will see that bounces from positive to negative value. And it's something you can try to play with. It's a very simple change in the code, which is adding here an x to the 4th term with a coefficient in front, right? And you can try to study a bit this thing. So as far as they are local, it's okay, yes. So right, I mean, you want the distance. I don't know if there are issues with that. I know the typical example here are the harmonic and harmonic oscillator. But it's still local, yeah. I don't know if it has issues with that, but one can try. Okay. Okay. If there are no more questions, see you tomorrow.